Hello everyone, this is DA from E Academy, and today this video is the second episode of the lemma that we have continued in the previous video. And this is the lemma that we have started, that if we have a bounded function and having a limit a b, and we have a partition p1 and the second partition p2 from a set of partition p such that p1 is a subset of p2, then this will be the relation that is the target. And we have proved in the previous video the relation of the supremum and infimum of a certain partition with the supremum and infimum of the function in the interval a and b. So we have seen this part of the proof in the previous video, that if we have this partition p1 having elements x0, x1, so on to xk minus 1, xk, and then towards xn, where x0 is a and where xn is b. So if we know the relation of the supremum of the whole of the function, supremum of the interval, and same case for the infimum. This is the infimum of the function, this is the infimum of the function within the interval, this is the supremum of the function within a certain interval with the kth interval, and this is the supremum of the whole of the function. So we know that m delta x can be written as, where delta x is the length of the interval, because we are taking the partition in between a and b, so that is why delta x, the length of the interval, is b minus a, and b minus a because whole of the length, so we can write it as a summation part, sum of the every possible finite or smaller elements. So here we have this mk. We know that m is smaller than mk, so this is the relation used here, and mk is smaller than capital Mk, the infimum is smaller than supremum, and this relation is used here, and every possible supremum is in between a certain interval is less than or equal to the supremum whole of the function within a certain interval, so this relation is used here. So now mb minus a is this part, supremum mk minus this is this part, and this is, and mb minus a is this. So this is the definition of the lower Riemann sum, this, and this is the definition of the upper Riemann sum. So we have seen this part in the previous video. Now we will look at this part. We will look at this part of this lemma now. So here we are with the p2, the second partition from the set of partitions, because it was given here that p2 must be greater than p1, or p2 must be a supremum, not supremum, but a superset of p1. So here we have x prime or x dash, an extra point from p1 here. So p2 is a partition that is not p1 but is the superset of p1, having x0, having an x1, having xk minus 1, but an extra point x dash from p1. So here the relation between p1 and p2 is that p1 is the subset of p2 and p2 is a finer partition of p1 here. And now for this we will talk about the supremum and the infimum of the function at this certain interval, when we're taking the values at xk minus 1 and xk dash, and when we're taking the values of x dash and xk. So let's write the notation. So the notations here are, when we're taking the elements from this interval xk minus 1 and x prime, so we have this interval, so the endpoints are also included. So mk prime is the notation for the infimum when x is taken from this, and mk double prime is the infimum when x is taken from this set, and similarly for the supremum, capital Mk prime, where mk dash is the supremum of the values of x that are taken from this interval, and mk double dash or mk double prime is the supremum of the function when x is taken from this interval x dash and xk. So now we know the definition of the Riemann upper sum, that is summation of mk delta xk, that is used also here for the partition p1. So if we're going to expand this, then this will be equal to, so this is m1 delta x1 plus m2 delta x2, and so on to the kth mk delta xk and then mn delta xn. And now look, if we're going to write the upper sum, Riemann upper sum for this partition P2, then this will be, so as we have added this point x dash in this interval in this partition P2, so that's why when we're talking about the Riemann upper sum, so by using this notation, we will have 2 points mk we have two product mk dash delta xk dash plus mk double prime delta xk double prime here, that are different from this partition. So now if we are going to subtract both of them, then this is obvious that we will left out with mk delta xk with minus mk prime delta xk prime and minus mk double prime delta xk double prime. So again, if we're going to subtract this, then we will left out with these three terms. So now we have this, and if we're going to expand delta xk, so this will be xk minus xk minus 1, and for the delta x prime we have x prime minus xk minus 1, and for the delta x double prime we have xk minus x prime, the way we have defined mk prime and mk double prime. So if we are going to multiply, if we are going to expand this and multiply mk with xk and then mk with all of them, then we will have the terms. So we have these expressions. And if we're going to add and subtract, mk x bar here or mk x prime here, so we're going to make the pairs, and we will use the definition of mk with mk double prime as well. So we're going to make the pair of mk, xk minus 1 mk x bar, and with m bar x bar mk x bar, and with mk bar xk minus 1. So we have pair of 4 elements here, and the other elements that are mkx xk and mkx dash. So we'll write the remaining elements. So we have these elements now with the pairing of elements with the additional mkx dash with and minus mkx dash. So now we will again make the pairs of two elements of the supremum, and then with the related or the corresponding differences of the interval. So here we have x bar xk minus 1, and we have x bar and xk minus 1. So from here we will take out mk common, and from here we will take out mk bar common, and same case for we will take common mk, and here we will mk double prime common from these two factors. So let's take it out. So now we have these. Now we'll apply again the formula. Then we will have mk minus mk bar, and then x bar minus xk minus 1, and for here we have plus mk capital mk minus mk double bar with xk minus 1, the common element from this. So as we know that when we're talking about the notation of m prime and double prime, we have defined mk prime and mk double prime such that mk is less than or equal to mk prime, and the same case that mk is also less than mk double prime. And this is the case where when we're talking about the capital mk, so this is less than capital mk, and this is also less than capital mk. Why? Because this is the general supremum for the kth interval when we're talking about for the certain partition P1 here. So this is the certain partition P1 here. So here capital small m1, here small mk is less than, should be less than this, the infimum that was taken from this. So that is why P2 is finer than P1. So and the same relation goes for the supremum, that here when we're talking about the supremum in the partition P1, the certain partition mk, that supremum must be greater than, when we're talking about this, the certain partition, the supremum between xk minus 1 and x dash and xk, so that supremum must be less than mk. So we will use the relation here that if we're going to make the difference of mk minus mk dash, mk minus mk dash is eventually greater than or equal to 0. So mk minus, and the same goes for the mk minus. Mk double dash is also greater than 0. So the difference is also positive. And this is the difference. So this difference is positive, this difference is positive, and we know that here this is x dash, this is xk minus 1, and this is xk. So the difference of xk, x dash, and xk minus is also positive, and the difference of xk minus x dash is also positive. So we have this positive term, we have this positive term, so this will be greater than or equal to 0, and we will now imply that. We will now imply a very important result from here, because this is the difference. This is the difference of SFP minus 1 minus this. So this, if the difference is positive, then we can imply that SFP1 is greater than SFP2. That is, the supremum from the not the supremum, but the upper sum from the partition P1 is greater than the upper sum from the partition P2. So the upper sum for the lower partition, the partition P1 is greater than the finer partition. So the finer partition, the upper sum of the finer partition will be more close to the actual sum or the actual area under the curve. So this is the very important relation, and similarly we can write it as the lower sum of FP2 is greater than SFP1. On the same lines we will prove that. So I'm not going to prove it, this is the task for you. So you can prove on the same lines that the lower sum of the finer partition is greater than the partition P1. Why? Because the lower sum was lower than the actual area under the curve. So the finer partition will be greater than the lower, will be this, and moving towards the actual area under the curve. So this completes our lemma. So these two relations complete our lemma. And now we will complete this. We will write the complete statement here. So we have proved this, that here the lower sum of the partition of the finer partition is greater than the lower partition, and here the supremum, the upper sum of the finer partition is less than that of the P1 or the subset partition. And that relation we have proved in the previous video. So now we have completed the proof of the very important lemma of the Riemann integral relating to the lower sum, upper sum of the finer partition with the infimum and supremum of it as well. So this is for now. Looking for more such videos, then you can subscribe this channel and you want to watch more upcoming videos. We will meet in the next video. Till then, take care. Goodbye.